So this is example number 4 of this NMR series explaining how to assign resonances to spectra. And if I look at this particular molecule here, I have two groups, a CH2, CH3 group, this ethyl group, and this benzene ring here. So these are all aromatic resonances, 1, 2, 3, 4, 5. And these 5 aromatic resonances, you know, because of diamagnetic anisotropy, they are in this region of the NMR spectrum. So because all the lines are so close together, I can't really differentiate and say which is C, which is D, and which is E here. So I can just say C, D, and E are in this region of the NMR spectrum. Right, and they are in a typical region for aromatic protons between 7 and 7.4. Right, so normally we can get them from around 6.9 to about 7.8 or so. So this whole region here, we can see aromatic proton resonances. We can't differentiate them in this case because they're too close together. You'll find, and I might show you an example later on, when I have a nitro group here, it de-shields some of these resonances because it's electronegative, and then these resonances appear different from those, and we can actually differentiate them in the NMR spectrum, but I'll show you that a bit later. So those are C, D, and E. Then the ethyl group that you have here, you can see now there's two distinct chemical shifts for this ethyl group. Alright, and I'll look at the splitting patterns first, because you can actually do this without looking at the chemical shifts, and I'll come back to the chemical shifts just now. But let's look at the splitting patterns. This CH3 should be a triplet. It's next to a CH2 group. So if I'm looking for a triplet, I can see a triplet here. That must be A. And this CH2 group being next to a CH3 group must be a quartet. I can't see it clearly, but they've expanded it for us here. You can see clearly it's a quartet, 4 lines. So this must be B. And now I want to revisit the chemical shift. And if I revisit the chemical shift, what you can see is that this resonance marked B with the CH2 is directly bonded to the aromatic ring where the diamagnetic anisotropy occurs. And that de-shields this resonance closer to 3. So normally a CH2 would be around 1.2 or so, and that de-shields it to about 2.8 because it's close to an aromatic ring or bonded directly to an aromatic ring. And that's the reason why it's de-shielded. The other resonance occurs in the typical region of the CH3 group, and we find that the CH3 group is at 1.2, slightly de-shielded because of the aromatic ring, but that aromatic ring is further away than the CH2 group, so it's not as de-shielded as the CH2 group. So just slightly so normally from 0.9 to about 1.2, so the slight de-shielding is because it's in the vicinity of the aromatic group, maybe 2 bonds away. So that's how we can assign this particular molecule. I have another one to show you in the series. I told you we can be able to distinguish between aromatic resonances, and this is the nitro example I was talking to you about. And let's look at why they've called that A, B, and C and not assigned that, because we know there's some symmetry in the molecule. Can you see symmetry around that axis here, which means this is equivalent to that, and that is equivalent to that. So if I look at these two protons here, and these two protons here, and that proton here, I just need to look at one half of the molecule and see that these are next to that. So this proton being next to that, this would be split into a doublet. This A that I'm finding here is going to be next to that C and that B. Right? So these two are non-equivalent. Right? So it's going to be split into a doublet like that you see here, and each of these is going to be split further into a double doublet. Alright? I'm just going to draw it like this for now, and I'm going to show you what happens in this particular example and in many other examples like this. So what you would see in this particular case is that these two inner lines, you can see these two inner ones here, because the coupling constant between C, so A and C would give you a coupling constant of about 8 Hertz. Remember I told you about coupling constants in double bonds. When we have cis protons or adjacent protons on an aromatic ring, the coupling constant is also about 8 Hertz. Right? So that coupling constant is also about 8 Hertz. And the coupling constant there would also be around 8 Hertz. But if they netted to each other, so this B and C, so A and C would have a coupling constant of 8 Hertz because they ortho to each other. A and B would also have a coupling constant of about 8 Hertz because they ortho to each other. Alright? And because they have similar coupling constants, these two lines now coalesce. And what we see is just one peak for those two lines because these are those two lines coalescing because of the similar coupling constants. So what we end up seeing is like a triplet for A. So A would give us a triplet, well, something that looks like a triplet, but you can see it's actually a double doublet with equivalent coupling constants. C we know would give us a doublet, right? And B you find is next to these two equivalent protons, so B would be a triplet. Right, so this would be a triplet. And if I look at my spectrum, I see a doublet and two triplets. Right, so this doublet is expanded here, so you can see that this is clearly a doublet. And these two are triplets, they expanded here, so you can see they clearly two triplets. Right, so at this point in time, I would be able to differentiate C from the other two. So my doublet must be C. And I need to now try and differentiate between A and B. Right? And I can easily do this using the integration. Because these two protons, right, should have relatively double the integration of that proton. Right? Now look at here, there's a 2:1 ratio. Here, 2 proton is to 1 proton ratio. So this must be B and this must be A. So I can look at my A protons, my B protons, and my C protons. Very interesting and something to note is that my most shielded resonance in this case is A. And that's when I have an electron withdrawing group here. Your most shielded resonance because of resonance effects is your meta proton. Right? So the meta proton A is more shielded, and your ortho and para protons are more deshielded. In the case here, you can see that your ortho proton is much more deshielded than your para proton in this particular case. Alright, so you learned something about how to differentiate between the protons on an aromatic ring here. You've also learned about coupling constants, orthocoupling. So orthocoupling on an aromatic ring is 8 Hertz. So between those two protons, 8 Hertz. Between those two protons, 8 Hertz. But we can also get something between the meta protons. So this proton is meta to that proton, right? So that's 3, 1, 2, 3, 4 bonds away. The meta coupling that I see here would be about 2 to 3 Hertz. Right, so you don't see it in this particular example because we have equivalents, but there might be other molecules where we can see it as doublets, and that would give you a very small coupling constant of about 2 to 3 Hertz. Alright, particularly if I have a molecule something like this. So if I had a group here, maybe OH, I can put another group here, maybe a methyl there, I'll put a chlorine there. So this hydrogen and this hydrogen each would be doublets with coupling constants of about 2 to 3 Hertz. Okay, so that wraps up the 5 examples where we looked at structures and assigned them to resonances on spectra. And in the next few videos we'll be looking at just spectra maybe a molecular formula, and trying to get a structure from that molecular formula and the NMR spectrum. Keep watching this space.